Welcome to today's episode, where we're diving deep into the fascinating world of distributed systems. As our technology landscape evolves, the demand for systems that are robust, reliable, and efficient has never been greater. We'll explore some key concepts, including consistency models, fault tolerance, and the delicate interplay between consistency and availability. By the time we wrap up, you'll have a clearer picture of how these elements interact within distributed systems and what that means for software engineering. Let's start with the foundations of distributed systems. At their core, these systems create an illusion of shared storage, allowing users to interact with data as if it were centralized. A key component of this setup is something called a register. Think of registers as the basic units of storage where users can perform read or write operations. They're essential building blocks for managing data in distributed environments. Now, when we talk about operations on these registers, we can categorize them into two types: sequential and concurrent. Sequential operations are those where one completes before another starts, ensuring a clear order of execution. On the flip side, concurrent operations overlap in time, allowing multiple processes to access the same register simultaneously. This distinction is incredibly important because it shapes how data is managed and perceived by users. Grasping these dynamics is crucial for building resilient systems that can effectively handle failures. As we delve deeper, let's shift our focus to consistency models. So, what exactly are consistency models? They define how data visibility and behavior are maintained across various copies in a distributed system. These models are pivotal in ensuring that users get accurate and up-to-date information, no matter where they access the data. There are various consistency models, ranging from strong consistency, where all reads return the most recent write, to eventual consistency, which allows updates to propagate over time. The choice of which model to use can significantly impact both system performance and user experience. For example, while strong consistency guarantees that users see the most accurate data, it might compromise availability during network partitions. Next, let's talk about fault tolerance, which is a critical aspect of distributed systems. Fault tolerance is all about a system's ability to keep functioning correctly, even when some of its components fail. This resilience is essential for maintaining service availability and ensuring a seamless experience for users. One of the main strategies to achieve fault tolerance is through redundancy, specifically data replication. By creating multiple copies of data across different nodes, systems can ensure that if one node fails, others can seamlessly take over without interrupting service. This strategy not only boosts reliability, but also enhances performance by distributing the workload across various nodes. As we explore the complexities of these systems, we encounter the CAP theorem, which highlights the inherent trade-offs between consistency, availability, and partition tolerance. According to this theorem, when faced with network partitions, systems must make a choice. They can either serve consistent data or ensure availability. This trade-off presents significant challenges for software engineers. In situations where availability is prioritized, users might receive outdated or inconsistent data, leading to confusion and errors. On the other hand, focusing solely on consistency may result in downtime, negatively impacting user experience and business operations. Finding the right balance between these two factors is essential for the success of any distributed system. To navigate these trade-offs effectively, we introduce the concepts of harvest and yield as flexible metrics for evaluating system performance under failure conditions. These metrics give us insights into how well a system can perform despite challenges. Harvest refers to the amount of useful work a system can accomplish during a failure, while yield measures how well the system maintains its performance levels. By concentrating on these metrics, developers can design systems that not only endure failures, but also adapt to changing conditions, ultimately ensuring a better experience for users. Ultimately, the goal of designing distributed systems is to provide users with a seamless experience that feels just like using a single-node system. Users expect quick access to data and consistent performance, regardless of the complexities that lie beneath the surface of distributed data storage and communication. To achieve this, engineers need to carefully consider how data is managed across nodes, ensuring that operations are executed efficiently and effectively. By prioritizing user experience and leveraging advanced techniques for consistency and fault tolerance, developers can create systems that meet the demands of modern applications. In today's episode, we've explored the essential concepts of distributed systems, including consistency models, fault tolerance, and the trade-offs between consistency and availability. We've discussed the significance of understanding operations on registers and the metrics that help evaluate system performance. As technology continues to advance, the principles we've covered today will remain crucial for building resilient and efficient systems. Thanks for joining us. And we look forward to exploring more exciting topics in future episodes.